So the audio ports on computing devices come in what I consider two varieties. Input, such as microphones, and output, such as speakers. In the Windows operating system, they're called recording and playback. For playback, the output, you have something like a speaker output and something like a headphone output. I don't know if these are different, because a headphone is generally going to be unpowered, as in driven directly by the port itself, and a speaker is going to have its own power source. Now, I'm thinking they may be the same, because the speaker needs more power because it's driving a more powerful thing, whereas the headphone is just in your ear. But they may be different, so we'll measure them separately. Today, we'll just do headphones. As for microphones, there's only one type, but there's something called phantom power, which may or may not be present and may or may not be used. We'll get into that when we do microphones. So we recall that I made that speaker cable breakout board, and I was kind of proud of myself for managing it. But with modern technology, I found something better, so as cool as it is to use the things you made, once you made them, sometimes it's time to upgrade. So what I have here is the equivalent of a breakout board, except it's screw terminals. This is apparently fairly common. I got USB as well. And also I already had a barrel jack one. So this is a regular TRS connector, tip ring sleeve, so it would be for a set of stereo speakers. One is the ground connection, one is the left, and one is the right. And then you just have 3 wires coming out of it, screw terminal in, and I plug it into my breadboard. And I can just plug this into whatever I want. Now remember the safety aspect of making sure I don't fry anything. I'm going to be doing measurements with my oscilloscope, which I guess I can go ahead and turn on, because that is a passive, as in it does not generate voltage, and high impedance, as in it has a high resistance so it will not draw any significant current, input, measurement tool. We can always reduce resistance, we can always add voltage if we ever need to, and we'll need to for measuring microphones. But in this case, we always start from a position of safety. Now there's one final thing to consider before actually doing the measurement. Am I connecting in series or parallel to whatever circuit is connected to that plug? And I'll say that it's almost certainly parallel. And the main reason for that is, if you recall, in series, when you have components one after another, they all have the same current, but they have different voltage drops based on their characteristics, such as how much resistance they have. Whereas in parallel, your 2 different parallel connections will have different currents going through them, but they'll both get the same voltage drop across them. So it seems weird to me that you would have any sort of thing that gives you a different magnitude signal based on the impedance of the output. And furthermore, the voltage drop changing based on the impedance of whatever you plug in would also affect the circuitry in the plug itself, if it's in series, because the voltage drop always has to add up to the power supply. Kirchhoff's voltage law loop has to be 0. So if we get more or less of a voltage drop on whatever we plug in, the circuit gets less or more on its parts, which can change how it functions. So I can't imagine it wouldn't be a parallel connection. So if it's a parallel connection, I can plug the oscilloscope right in as the load, because the oscilloscope will measure the voltage drop across its probes regardless of how much resistance are in the probes. But if it's in series, then it's going to make a big difference if we plug in an 8 ohm load or a 10 mega ohm load. So let's just operate on the principle that it's parallel. So I'll plug this into my breadboard, and we'll start with a tablet. So there's my oscilloscope screen, currently showing nothing, of course. That's just whatever it's picking up out of the air, which will change as I touch it. So I'm setting up the yellow lead in one set of traces, doing a double check to make sure I've plugged it in correctly, the green into another set, and then I'm going to use one jumper wire on the breadboard to make sure that I have connected the grounds together. So going by the labels on this breakout board, I will put the L as the positive of one probe, the R, and you can see it changed because now it's acting as a bigger antenna when I touch the tip, the R as the positive of the other trace, and then I'll just plug the ground into one of them and it'll share between. So now you can see we have a nice unified signal when I touch it, and then I will plug it in to my tablet. Now, one tricky thing here. These devices, when you try to plug something into the headphone port, it detects that something's there. Normally it outputs to its speaker, but when you plug it into the headphone port, you may notice that it mutes the speaker and plays to the headphone. Well, the problem there is this is not a standard setup, so it's got imperfect detection. So when I plug it in this case it looks like it did a great job. We got a nice flat line now, I'm wiggling it all over, and there's no more noise coming in because it's connected to the positive, or I should say affirmative, power source of the battery in the tablet. So let me just open up the settings here and go to the sound and notification, and I'll try to play a notification. And that's interesting, it played through both. Can you see? Watch this. I'll play it now. I'll even do a freeze frame, so we'll do single, and when I play the notification, you can see it starts to get a signal. If I reduce the time and do a capture again, see, we're getting a signal. This is the audio. I can even separate, you can see the two different channels, so it's not the same left and right, but it's still playing the audio through the headphone port. So this is interesting. Apparently, it always puts a voltage across the headphone port and its own speakers, and it just mutes the speakers if it detects a headphone. That's how this device appears to work. I bet that saves on some circuitry. So let me get this live again, like that. So if I change notifications, you can see, and possibly hear, let me turn my volume up as much as possible. Okay, the volume is at maximum. But as I go through these different notifications, you can see on the oscilloscope the little signals going by. Now, I have the tablet at absolute maximum volume. It's giving out all it's going to give out. So what I'm going to do is try and shrink time again. Let's see, let's measure 100 millisecond separations will give us half a second, but if I move this over, I move the 0 point, so the 0 point's on the left instead of the middle. So now we're roughly going to get 1 second. So whenever I do single to capture and play a notification sound, you can see that it recorded the notification sound, and I can zoom in a little bit, like this, and I can get an idea of the magnitude here. So every separation is 50 millivolts. So 1, 2, 3, 4. So that's about 200 millivolts up. And, of course, 1, 2, 3, 4, 50 times 4 is 200 millivolts down. So about 400 millivolts peak to peak. Let me try a different notification sound. Oh, and it picked up noise. It's picking up noise. That's interesting. So let me run. Oh, so that's much louder. So let me try single and get that in there. There we go. I had to be quick because the noise is actually loud enough that it's detecting that as a signal. I can configure that in the oscilloscope, but it's not that big a deal. So we can see this one is a little bit louder. So let's bring the scale down a little bit. So now each division is 100 millivolts. So 1, 2, 300 or 250, but it looks like it's a little bit past the halfway point. So let's say 300 and 1, 2, it could be 250 or 300. So we're looking at about 500 to 600 millivolts peak to peak, from 0 to about 250 to 300, so peak to peak is about 500 to 600. So let's do another one. Let's do this one, and we can see it's a different signal. How about this one? Or this one? There we are. How about this one? So we seem to have consistency now. All of them seem to be about the same height. So 10, 20, 25, 250 millivolts to 300 millivolts. So I'm going to say for this device, the signal, the expected range at maximum output volume is, oh, and if we look lower here, 10, 20, 30, and it's a little bit past, so maybe we want to say 400, so 800 peak to peak. Generally, I'm seeing signals that go to about 250 millivolts, smidge over maybe 275, but this one does dip down to about 350. So if I were engineering something, I would say, well, why not just make it 1 volt peak to peak? That'll definitely include all these signals, and it's nice and safe. Because there's another factor here. This is the maximum output volume, but do we know that it's the maximum output audio signal? Maybe the signal is not completely maximized. Remember yesterday I showed you? Maybe it's not getting all the way to -1 and 1. So a tablet is rather more limited in what it can do. So I'm going to go ahead and unplug that, and I'm going to just turn that off. Let's say we're done with that for now. And I'm going to switch to a laptop. And the nice thing about this is it's running an actual normal operating system, Windows in this case, and I can use a program called Audacity. So it may not be easy to see, but I'll just try and give you a bit of an angle. Here, let me just zoom out for a moment. So this is my laptop screen, and you should be able to see on it this waveform. It looks like a sine wave. This is the Audacity program, and I have an audio file file opened up. The bottom of the screen is -1, the top of the screen is 1, just like yesterday. So that is an example of those digital audio files being edited directly. So for example, I have one here that is a 600 hertz sine wave. I'll try and play it so you can hear it in the microphone. See that tone? Can you hear that tone? So let me stop that. In the Audacity program, the actual digital file, I generated that sine wave to be the full height. It goes to -1, it goes to 1, as I mess up the focus apparently. It goes to -1, it goes to 1. It is the full, I have verified, full magnitude, amplitude. And the Audacity program, the audio player, is currently set at 100% volume, so it's not modifying the file, it's outputting it directly. In Audacity, you can actually bring it below or above 100%. But if you bring it above 100% and the output's already 100%, it's not going to change anything. But if you have your volume lower, let's say the audio file is very quiet, you can actually raise the volume above, like this signal, for example. Let's say this is -1 to 1. 100% volume would be this, but if you had 200% volume, it might be up here. So going over 100% is meaningful when your signal is quiet. But then the actual laptop volume was something like 60% because the laptop has a pretty strong speaker in it. But now I'm going to plug it into the oscilloscope, and we don't have to hear it, so I can turn the volume all the way up. And we won't be waking the dead. And of course, I have ripped it out of my breadboard, so let's fix that. Now, like I said, it's a little bit of a finicky detection, because whatever mechanism it's using to detect that something's plugged in, I think having a 10 mega ohm load that's not actually a speaker or headphones is messing with it. But let's see if it worked. Where's my mouse? There we go. Let's open the sine wave file again and see if it comes through the speakers. And it's not. You can see this just grew rather significantly. Let me actually expand the time. So there we go. Let me get it bigger so it's nice. There we go. Now it's happy with me. So if I can separate this, you can see there's a left channel and a right channel, but I'll just put them in the middle because it's pretty much the same signal. So this, and I can even freeze frame and you can see it's nice and smooth. This is the 600 hertz sine wave. And I will now turn the volume up and down in the actual audio settings for my laptop. So if I turn the volume up, and it's warning me that high volumes on headphones can allow hearing loss. Yes, I know, sweetheart, it's not a headphone. But if I turn the volume up and down and up and down, you can see the signal changing up and down. That's me changing the volume of the speakers in Windows, just a little volume up and down knob. Let me go ahead and do that in Audacity instead. So if I turn it down and down, you can see it shrink. All right, I turn it back up. But now I'm turning it up over 100% and nothing's happening. You see I'm above 100% and it's wiggling and nothing. And then I turn it down, 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 up, up, up. But if I go above 100%, up, 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 nothing, down, 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 nothing. This is because my audio file, it's more like this. My audio file is actually going to the absolute minimum and maximum. So if you try to go over 100%, it won't let you because it detects, oh, if you try to go higher, it's going to start cutting off pieces, see? But I could go over 100% if it was like this and there was headroom to expand. So let me turn the volume of the laptop all the way to 100%. Up, 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 and there's 100. Audacity, or rather in this case VLC. I keep saying Audacity, I'm sorry. The player is called VLC. So yeah, Audacity is the audio editor, which can play, but I'm using VLC to play. But also, so the audio file uses the full amplitude range, -1 to 1. The VLC volume is at 100%. The system volume is at 100%, so it's sending the signal completely unadjusted. So now, let me shrink down until I can see it. Make sure it's centered, make sure the time is centered, and now we can see our nice 600 hertz sine wave. We can verify the wavelength. So right now, if I have 1 millisecond dividers, then it is 1 millisecond to about 1.5, 1.6, about 1.6 milliseconds from the start of a wave to the start of another wave, which is about right because 60 hertz, I've memorized this value because of programming. 60 hertz is about 16.67 milliseconds. So 600 hertz would be about 1.67. So there's our 600 hertz frequency. What about the amplitude? The divisions are 200 millivolts. So 200, 400, 500 to 600. And this one's about the same. So with absolute maximum volume, I'm getting about 600 up, 600 down, or 1200, 1.2 volts, peak to peak. And we can see that clearer if I change, not that one, this to 1 volt. I suppose half a volt would be more useful. You can see from the midpoint half a volt up and half a volt down, it is dipping just below and just above. So this is about 1.2 volts peak to peak, so that's much more than expected. Now, if you recall the amplifier, remember the emitter resistor that we usually assign about 1 volt to? For this one at maximum volume, that would actually not be enough because the value of that voltage drop varies. If we set that at 1 volt when the signal is at 0 and it's, let's say, 500 millivolts up and 500 millivolts down, that resistor would have a 1 volt drop here, a 1.5 volt drop here, and a 0.5 volt drop here because the signal is changing that. If you wonder why it's going blank every once in a while, that's just because the audio file is restarting. I've got it on loop. But we can see here, if we have about 1.2 volts peak to peak, we're going to need to set that resistor closer to, let's say, 2 volts. And that would definitely handle it. And then we definitely want to have a higher power supply as well, so maybe 12 volts. So we established that we were getting about 500 to 600 millivolts peak to peak from the tablet. But I could not confirm that I was outputting maximum signal value. On here I can. So maybe the tablet would put out higher. It's entirely possible those sounds were just too quiet. Now, here's another thing. Let me get rid of this sine wave. I have another file which is silence, and you'll see it's just 0. Now if I bring it up, of course you can see that there's noise. This is only 5 millivolts. So the magnitude of our noise, let me bring it down to 10 so it's a little easier to see. So about 15 to 20 millivolts of noise. That's not terrible. And keep in mind, I'm putting this through a breadboard. The vast majority of this noise is those breadboard wires acting as antennae. If you have a nice speaker wire that's a little better insulated, or even better, you're doing some twisted pair thing with high fidelity audio cables or whatever, this is the noise that's getting rid of. But it's like, what? 10, 20, 40 to 50 to 60 even millivolts peak to peak compared to the hundreds millivolts. So signal to noise ratio at least 1 to 10, or I guess 10 to 1 signal to noise. That's fine. Probably won't be able to hear that too much. But in any case, that's the noise. So let me bring this back up to a more useful value. And you can see that, of course, I'm getting a 0 signal when I'm outputting silence. Now, I'll do something more interesting. I have created a square wave, but I've created a long square wave. So now, this is 0, 2, 4, 5-ish, 2, 4, 5-ish. So we can see we go up here, 200 millivolts. So let me set it to the top again. So about 2, 4, 5, 550, close to 600, and down here close to minus 600. See, it's a very long cycled square wave that's switching up and down and up and down. It's just flat lines in Audacity. So we can see this is definitely where the voltage sits. Now, why did I do this? Because I want to actually measure the current. Because it's not enough to say, oh, we're getting a voltage signal out of this. Well, no kidding. We knew we would have that. Right now, we've verified the range of voltage. That's useful. So we can say that, maybe 1.2 volts. So let's just say 2 volts. Let's expect we're going to get no more than 2 volts and probably less, but we'll pick 2 volts as a safety that we need to handle. 2 volts peak to peak, so plus 1 volt, minus 1 volt. And again, I'll shrink it down so that 1 volt, see this divider here between my fingers is 1 volt, and you can see that it's going up and down at absolute maximum volume at less than plus 1 and minus 1. So 2 volts peak to peak should be safe. But now it's time to whip out the multimeter. So I'm actually going to turn off, I'm going to unplug the headphone, and I'll go ahead and plug that back in later. But let me turn my oscilloscope off, because now we'll be using the multimeter. Let me just get that set up. So here is my multimeter and breadboard. My multimeter is on the voltage setting right now, which is the same thing that an oscilloscope does. So this is a passive high impedance scan, still safe. So I'm going to, as a diagnostic, just set this back up, go ahead and plug in the headphones again, hope that connected, and I'll test to see if it connected by playing the 600 Hertz sine wave. And indeed, it is not playing it on the speakers. Thankfully, because I forgot to turn the volume down. So let me get rid of that, and instead, I'll open up the square wave. So we can confirm that the load actually doesn't matter for the detection. I have no load plugged in. It's an open circuit. It's physically plugged in, but it's an open circuit between both the left and right conductor and the ground conductor. So what's probably happening is it's detecting the physical presence of metal in the plug, just testing for capacitance or conductance or something to say, hey, something's plugged in, mute the speaker. So I will now use simple jumper cables, and I'm going to connect just one side since I have only one multimeter set up. So just one side, the L side in this case, to the multimeter, and we can see negative 0.08, and if we wait, it switches to 0.08. So I'm getting my square wave back and forth. Let me switch to a more sensitive voltage reading. So now we're on millivolts, 87 millivolts. But if I do 200, so right now I'm getting minus 87 and plus 87 millivolts. That's interesting, because we were certainly getting more than that on the oscilloscope. But once again, this load is connected in series with the plug. So I'm wondering, am I measuring wrong? Or was I wrong about it being parallel? I might be wrong about it being parallel, because this, I don't know what the impedance is. I can't measure its own impedance, unfortunately. I need another multimeter for that. But this may not be 10 mega ohms. Interesting. But now, instead of that, I'm going to plug in an actual potentiometer as a load. The reason I'm doing a potentiometer is I want to try and turn that load down as much as possible. So which one do I have here? 502 is 5K. That seems a bit much, considering my headphones measured at 30 some. So I'm going to use just a 100 ohm potentiometer. So I've decided this is safe because I've measured my headphones. They're very low impedance, comparatively. But to be even safer, I'm going to make sure that this potentiometer is turned up to 100 before using it. I don't want to accidentally short something because this is an expensive laptop. So the first thing I'm going to do is measure the potentiometer. Let's put this in ohms mode. So I'll connect the potentiometer across the multimeter, plug the multimeter back in. I don't know why I unplugged it. And so I'm measuring about 28 ohms. Let me turn it all the way up. And I'm only getting about 27, 29 ohms on what's supposed to be a 100 ohm potentiometer. Oh, aha. I apparently have it wired backwards. Hold that thought. Yes, I have it wired backwards. This is why we check. This is why we check. So let's try that again. So I'm getting a high value, if I turn it all the way up, of about 127, all the way down of about 27. So even at 0, this is not 0 ohms. That'll be all right, as long as we know what it is. So let's remember we're getting roughly 26 ohms at the lower end. We can calculate current from that. So first I'm going to turn it up. So we get a little over 100. And now I'm going to plug it not across the multimeter, but across the signal. Make sure nothing explodes or catches fire. Seems all right. So now I'm going to insert the multimeter in current mode now, into this circuit. So now the multimeter should have almost no resistance. So let's say that's going to be a negative connection through the resistor. And we'll do a positive connection to the positive terminal of the multimeter. And the current we're getting here, oh, that's microamps. Well, that's all right. I accidentally had it set on micro instead of milli. So minus 374 microamps to 375-ish microamps. So we're getting our nice square wave. So now I'm going to very slowly and carefully turn down this potentiometer. We should see the current go up, and we are. But what I'm doing is just making sure that it doesn't go too high. Nice and gently. You know, a milliamp or two, no matter what, is not going to hurt anything. I've turned it down most of the way. So now we're up to about 600, so 0.6 milliamps. I'm going up a little bit more, or rather down on the potentiometer, 655, and I've reached a limit. So with only 27 some ohms of resistance, we're down in the microamp range. So let me turn my tablet back on, actually, so I have a calculator, and let's do a quick calculation. Our good friend Ohm says if we have resistance and current, we can get voltage. If voltage equals current times resistance, there you go. So let's open up my calculator, and I'll say that 655 milliamps, and this is an accurate measurement, that's why I made a square wave. It's effectively a DC signal. It's not measuring a changing signal, it's a DC signal. So 655 divided by 1 million, that's 6 zeros, 0.000655 amps, times about, let's say, 27 ohms, equals 0.0176 volts, so it went down again. So it actually seems like I was very wrong. It must be a series connection, because this is in current mode, so it's not really adding any significant resistance. The lower the resistance of the load plugged into the headphone jack, the lower the voltage drop, which is exactly as we would expect if you recall the series resistance formula. So there must be a resistor, naturally or artificially, probably naturally, in the output port, so that if you short across, it's not going to hurt anything. And I'm going to be brave. I'm going to short it across. I'm going to remove the resistor, and I'm going to go ahead, and this does have a fuse, so if it draws too much, hopefully this fuse will burn before the laptop does. But if I plug directly across, 691, 692 microamps directly shorted across the multimeter. Because now we have, what, 1 ohm, 2, maybe 3 with all these wires I've got? So I reduced the load again. There you go. So this answers another question as well. So if you recall, we have our TRS, tip ring sleeve. This is what's plugged in. But remember a mono microphone? It might just be TS, tip and sleeve. Only one conductor plus ground. But it's the same plug, the same size, and they're compatible. You can plug a mono into a stereo and a stereo into a mono. If you plug headphones, stereo headphones into a mono output, you'll just hear something in one ear and not the other. You see the little black rings? These are what separate the conductors. If you have only two conductors, then you'll have only one black ring, this one. And this one, the one closer to this side, just won't be there. So look at this. This is ground. The sleeve, this end is ground. This, I believe, is right and this is left. It doesn't matter. One of these is left and one of these is right. And this back here is the ground. If this black conductor here, the one further towards this end, is not there, you're shorting ground and one of the sides. You're straight up shorting them together just by plugging this in. And you have to believe people will make mistakes, or people will just do it on purpose. And you have to believe that you wouldn't let that fry your circuitry. And we're right. There is output impedance that prevents that. So if you plug a TS into a TRS, or a TRS into a TRRS, you're fine. See? There you go. So the good news is, I got the answers I needed. I have a rough voltage range to work with, but it's not the answer I expected. And I'll need to be doing more testing. But the point is, what I have is a safe upper limit. That 2 volts, I'm still going to go with 2 volts. Because it may be that I want to plug it into a high impedance analog pin of an Arduino, rather than an actual speaker. But the interesting part was discovering it's actually a serial connection. I would not have expected the circuitry to work that way, but apparently it does. So perhaps they have the same setup that I expected, except they've broken it off so that in parallel with its circuitry, because remember I said the changing voltage of different parts of the circuitry due to the changing resistance of what's plugged into the circuitry, that's still an issue. But if their circuitry is connected in parallel internally, like you've got whatever the audio circuitry is, and then in parallel, you have, let's say, a trace on a PCB, a resistor, and then it's connected to the port, and then the other end is just connected to ground. So they just have that broken off. So that's a parallel connection, but then I plug into series with that. So I slot into that little break off. So they have a nice parallel separation from their circuitry. Wouldn't that be interesting? Apparently my upstairs neighbors think it's interesting as well. So this information is quite interesting, and we'll be using that in the future. But for now, I have to go digest it. And while I do that, I'll be seeing you.